Hello. These are the notes that we missed today because of our snow coming in. Took me some time to get home. So this is writing polynomial functions. We've done a lot of factoring of functions, knowing how many zeros we can find of functions given in standard form. It's the highest degree. So that's kind of what the fundamental theorem of algebra tells us, is if we have a degree of n is always a positive degree, it's going to have at least one zero. Real, or it could be imaginary, and it could be in the complex number system. So we'll see furthermore, complex number system is a plus bi, a plus or minus bi. And we were able to find zeros like that when we took square roots of imaginary numbers, and so on. We also had repeated zeros. Those are ones that are with multiplicities. And we'll see that today. All right, so for the following function written in standard form, we're going to write the polynomial in factored form. So we've seen this. We've done factored form. How do we factor this four-term polynomial? Grouping's probably a great idea. So we're going to group these, and we have x squared, x minus 4, and then a negative 1 is going to come out, and we have x minus 4 left on the inside. We consistently keep this f of x here because we are just writing the polynomial function in factored form. All right, so f of x is equal to, that's x squared minus 1 and x minus 4. This x squared minus 1, though, becomes x minus 1, x plus 1. Right? Remember to always factor those differences of squares. So we've actually been able to graph this function in both standard form and in factored form. So today we're going to go from this using zeros, given zeros, back to the standard form. That's writing, so factored form here, standard form here. All right. Write a polynomial in factored form that could represent each graphed polynomial. All right. So just any polynomial, we're disregarding our y-intercepts. We'll see down the line that changes some things if we have a different y-intercept than our final. So what are the zeros here? And do we have any multiplicities? We got this guy, and this guy. No multiplicities because it doesn't bounce. We see over in B there, there's a bounce off of the x-axis. So our zeros here are negative 2, 2, and 8. But if I need factored form, I need these zeros to be factors. So the factors, I'm just going to go down here and write my f of x. That's x plus 2 would be the x minus, or the negative 2, x minus 2, and x minus 8. And that is factored form. Now, is it the exact factored form? Down the line, we'll see that we might have to multiply this to something, might have to have something out in front of here in order to create this exact one. All right, and again, that direction here, that could represent the function that's graphed. All right, so this next one here, zeros. I have negative 3, 0. Looks like we got a multiplicity there, and positive 3. So negative 3, 0, multiplicity of 2, and positive 3. So what do those look like as factors? x minus 3, and again, I'm going to write those in factored form, x plus 3, and then we got that x squared because of this multiplicity of 2. So factored form, x squared, x minus 3, and x plus 3. And I know how to graph this from our previous quiz. Those zeros, it's a degree of 4, it's positive, there's a positive coefficient out in front of here. All right, moving on, this is again in factored form. So the complex root theorem, if a plus bi is a root, then a minus bi is also a root. So those are complex conjugates. So conjugates. This guy and this guy are conjugates of each other. And again, I write it as a plus or minus bi. And today we're going to see a lot of them are just in plus or minus bi form. They're easier to, way easier to multiply out. So again, if we see an imaginary solution given, we're going to need its opposite also. That same thing goes with irrational roots. If I have the square root of a, I'm going to need the negative square root of a. Why? Because if I have x squared is equal to, let's say 16, that's plus or minus 4. I'm sorry, that is plus or minus 4. But let's say, get you a 7 there, right? That's going to equal plus or minus square root of 7. So if I have square root of 7 as a solution, negative square root of 7 will also be a solution. All right, write a standard form polynomial function of least degree with real coefficients that has zeros, -2 and -9i. What does this mean, standard form? We should know what that means by now. But of least degree, so right now I have 2 zeros, so I know it's going to be at least a degree of 2. And then real coefficients, that means I don't want any imaginary. No imaginary coefficients. And that would just look funny because we've never seen something like that, right? But I do have these zeros here, and one of them is imaginary. So if I have zeros of -2, -9i, when I find -9i, it came with a positive 9i too, because again, plus or minus 9i. We're going to use something that we learned in Unit 0, where we have to use I squared here, because we're going to multiply these out. So now that we have these zeros, maybe I'll write it out and say, okay, what are the factors? We got an x plus 2, x plus 9i, x minus 9i. And if I write the polynomial out now, f of x is equal to x squared, x plus 2, x plus 9i, and x minus 9i. Again, I just rewrote that, but what we're going to need to do is actually FOIL it out. Best bet is to start with these guys, because that's nice. X squared minus 9ix outer plus 9ix. Those outer and inner terms will always cancel because these are conjugates of each other. And then minus 81i squared. All right, this stuff just drops down. I'm eventually going to multiply this x plus 2. All right, this becomes x squared. This guy right here becomes plus 81. And again, if I recall, this is negative 81 times a negative 1 because I squared equals a negative 1. All right, so now I have this stuff to multiply here. First outer, inner last. First is x cubed. Outer. I prefer to do the inner first because that's going to change it to standard form, but I'll go ahead and do foiling process there. First, outer, inner, last. And then I'm going to rearrange that to make it a nice standard form. That means decreasing exponential order. And you see we have all real coefficients. And the highest degree is 3. And I was given 2 zeros, but one of them was complex, so it has its conjugate. All right. This is my final answer, folks. As a function. We're going to do this again, but now we got a lot more zeros here. Write a standard form polynomial of least degree with real coefficients that has these zeros. So if I start with the zeros, -8, 4, those are real zeros, but this guy here is an irrational. So again, if I have positive square root of 2, it probably came, well, not probably, it did come in a pair of negative square root of 2. So again, x squared plus 2 equals 0 would give me these solutions. All right, so I'll go ahead, I'll write out factors. And you could go ahead, I prefer to just start it as f of x is equal to x plus 8, x minus 4, x minus square root of 2, and x plus square root of 2. All right. Best processes is to multiply these and then multiply these guys. Actually, I'll start with these guys and then do this. It doesn't really matter. You'll get a trinomial with the orange too, and then a binomial with these green turquoise ones. So we know that this guy, my outer and inner terms are going to cancel. That's like x square root of 2 and negative x square root of 2, and then negative square root of 4. I said x squared plus 2 earlier. This becomes x squared minus 2. Those middle two terms, again, will cancel out. I'll go ahead and FOIL these orange ones. X squared minus 4x plus 8x minus 32. And that becomes x squared plus 4x minus 32. F of x needs to keep coming down because we are writing a function, so we want function notation there. Again, best practices is to multiply these two guys into the trinomial. You can do the trinomial into the binomial, whatever works for you. For teaching purposes, I am going to just write out this, and then it gets multiplied to everything on the inside here, right? So we got x squared times all of this stuff. Then negative 2 times all of the stuff in orange. All right, we'll make those distributions there. And then combine like terms. Again, you can always pause this, work this out, and then check. And if I make a mistake, let me know too. All right, looks like I have these squared terms to be combined. And again, the practices that I show you typically it'll nicely align in standard form for us. And that is our final answer. Degree of 4, I was given 3 zeros, and then an irrational 0 comes in a pair, so that makes it 4 zeros. And oh my gosh, I saw that I wrote 4 there. All right. Another one here. This time it has a multiplicity of 2, with the 0 being 1, and then we got another imaginary 0. So imaginary, complex, imaginary, needs its opposite. So we got negative 4i is a 0. And we also have 1, multiplicity of 2. I didn't write that those are like my zeros essentially, along with the 4i that was given. All right, so let's set this up as a function in factored form. X minus 4i, x plus 4i. Doesn't matter what order we write that in. And then x minus 1 makes a 0 of 1, but we need that to be squared. And maybe I'll rewrite these to match those. All right. No, I don't just distribute this. I need to do x minus 1 times x minus 1. And then I need to FOIL these two. So I'll go ahead and FOIL this guy and then come back and FOIL those. So I know that the inner and outer terms are going to cancel, but for teaching purposes, I will write those out. And that becomes negative 16i squared. And if I keep going, those middle terms cancel out. X squared plus 16, because that's negative 16 times negative 1. All right, and then I'm going to have this stuff right here FOILed. Plus 1. So then I have x squared minus 2x plus 1. Final tedious step here. I have x squared times everything on the inside of that trinomial. And then positive 16 times everything on the inside of that trinomial. All right. Go ahead and FOIL those. And then I need to combine those. Oops. Going a little too fast here for myself. That's 17x squared. Degree of 4, I was given a multiplicity of 2 counts for 2 zeros. So that's 2 zeros for this guy. And then 3 4 zeros. And a degree of 4. All right. So how do we write these given this is write a function in any form that would match the graphs shown. So the ones that we did up here, could represent any of this. So again, without taking into consideration what our y-intercept is, just the zeros. Here, it has to match this graph. And so if it needs to match this graph, I need to take into consideration the y-intercept that's given. So the last time we started these, we started with the zeros. So what are our zeros? And this says write it in any form, so factored form's been great. And let me just start by saying the form that I'm looking for is I need to find this a. This a is some scalar multiple, like a shrink or a stretch, that will make this graph look as is. I'm going to say x minus p, x minus q, where p and q are zeros. Okay, and then again, that's in factored form, essentially. We are looking for a. That's what we need to find. So coming back to here, we have the zeros. I need to find that a. So I have a p, I have a q. One has a multiplicity. That's going to tell me something. So let's first write the zeros out. I have -4 and 1 multiplicity of 2. And I also have a y-intercept of 0, looks like that's 20. It's going by 20s. So if I were to write a general factored form polynomial, and I don't know what my a is, I would have x plus 4 and x minus 1 squared because of that multiplicity of 2. All right, but I was given this y-intercept, which f of x is also y. So I know a y, I know an x. I'm going to plug in 20 for my f of x and 0. I'm switching up colors here. 0 for my x. So 0 into here, 0 into here. And I'll solve for my a. So 0 plus 4 and 0 minus 1 squared. All right, essentially what we have here is 20 is equal to a times 4 times -1 squared, which is 1. So yeah, I could rewrite that as 4a, or you don't need to. You can just simply solve a is equal to 5. So my final answer, f of x is equal to 5 times x plus 4 times x minus 1 squared because of the multiplicity. So just a little step further in writing those polynomials, finding that a term. And typically our a has been 1 or negative 1 for the most part. We have seen some of the other ones where our a was not when we first started graphing polynomials. All right. Let's go ahead and check this out. Same idea. Zeros. Looks like I have negative 1, multiplicity of 2, and 3, multiplicity of 2. I have a y-intercept of 0, negative 30. So again, if I write out this general form, I need to find a, and I'll have x plus 1 squared and x minus 3 squared. But I need to find a. F of x is also y. I know a y is negative 30 there. And my x is 0. All right, let's keep solving here. Negative 30 is equal to a times, oops, I forgot my squared on that 1, even though it might not matter. It doesn't matter. I'm driving myself crazy with these colors. 1 squared and negative 3 squared. So in my calculator here, or you can use your calculator to negative 3 squared is 9. 9 times 1 squared is 9. And then is equal to 30 divided by 9. A is equal to, let's reduce that. 3 goes into that. 10 thirds, negative 10 thirds. And you know what's great about that is our A there being negative and it's facing downward. That kind of checks out, doesn't it? Yeah, it sure does. F of x is equal to negative 10 thirds. And then go back up to this guy, the yellow, and just fill in the A. That is my final answer. Writing polynomial functions. They're nice. They're nice and fancy. Factored form is always the nicest, but a lot of things are given to us in standard. All right. By all means, pause and come back if you need some extra help.